So in this law here, we have circumference you can spell it right, is directly proportional to diameter. I'm going to lower the font here. And can't change my colors here apparently. That is probably the shortest and sweetest way to pitch it, is that circumference is directly proportional to diameter. And I just went through describing, I think to all the groups, why is it that circumference is dependent. And so hopefully you recognize that anytime you say this is somehow proportional to that, you're also saying that this is the dependent variable and that is the independent. That's necessarily the case. So you have reasons why you would determine why one is independent and the other is dependent. And sometimes it's very straightforward in either direction, and other times you have to dig a little. So two reasons why circumference is the dependent is the way that we define a circle. It's literally defined in terms of its radii or diameter. Also, if you pull the line segment called diameter out of the circle, it can stand alone. It doesn't need a circle to be that line segment, but the circle has one and only one line segment that's fundamental to it. No other line segment, even if it crosses that circle or is tangent to it, none of those segments are fundamental to the circle. They might be associated with it in some way, but they're not fundamental to it. So in that sense, a circle does depend on its diameter. That's why a change in diameter always requires a corresponding change in circumference. It does go the other way, but we can't establish a dependency. All right? So the change relationship between circumference and diameter, it is a two-way street. If I change one, the other one changes with it. But a layer down, the diameter is independent of that circumference. That's tricky. Sometimes it's tricky. Other times it's just straightforward as the sun in the sky. All right. So we have that one. So now it says in symbolic language, algebra, write an identity for each measure. So that would be circumference equals circumference, diameter equals diameter. Then it says turn your identity for diameter into a fancy form of 1. Well, we just did that. Divide both sides by d, and you get d per d equals 1. Multiply the right-hand side of your identity on circumference, or the dependent variable, by your fancy form of 1. Now, all we've done at this point is preserve the identity on the dependent variable. What we need is for the axiom to encode what the law describes. And the axiom, that's what we have down here. This is our axiom. But it doesn't quite yet encode for what the law describes. So that's why in step 5, I tell you to move the denominator from your fancy form of 1 to be in relationship with the circumference. Because my statement of law demands that there be a connection between circumference and diameter, and the quotient relationship allows me to specify a this per that relationship. When it was still a product tied up with the fancy form of 1, circumference and diameter were not in relationship with one another. A product relationship doesn't encode for what we're after, but a quotient does. Now, I suspect that you guys have a sense that C per D is going to be equal to what number? What do you expect C over D to always be? I expect it to be pi. You would expect that for two reasons. You recall from some past experience that pi is defined to be the ratio of circumference to diameter. That would be a recall of fact. Or you might say, you know what? I remember the formula C equals pi D. C over D must be pi. You know, so that's all recall. Here's why this is important, this method, which is, good grief, we're doing arithmetic, low-level algebra maybe, right? But we turned a set of observations. We parsed out an empirically familiar regularity, and that was where the hard work was. Sorting that out conceptually, that's what was difficult. Writing identity statements and fancy forms of one and shifting a denominator around, that is insanely trivial, especially for a group of calculus students. At least I would hope, right? But what we have here is how right here, whoops, I need to switch to highlighter. This is where the axiom encodes for what the law describes. That piece of the axiom is setting up this connection between circumference and diameter. So if anything from this you learn, quotient relationships are how I encode mathematically for the connection between physical quantities. And if I can define in words how something is proportional to something else, I am expecting that to turn up in the form of a quotient. Here's the other thing about this method. We took an entirely theoretical approach. We had a hypothesis, we had a set of hypotheses about circles. This is greater than that all the time. A change in this always results in the change in that. All these hypotheses that are born out of experience and just logic. So we're entirely theoretical, and we said, you know what? What happens if I do some arithmetic on this? Now I'm at a spot where this is telling me what the experiment is. One of two things happens at this point. This factor that I've highlighted, either it's a constant that your experiment will deliver to you every time I do a quotient of this to that for an object, I get the same value. If you get that, then this is a number. This will be a constant. And sometimes the constant will have units. This time it won't because it's length per length. Sometimes our constants will have multiple, like Newton's gravitational constant has, 3 variables. Okay, that's different. So now this directs our experiment, which is what is next.